Okay, so here we are with our next set of reactions, and this time we're going back to our alkanes family, so looking at saturated hydrocarbons and single bonds only to carbon, and we're going to look at the type of reactions that they undergo. So hopefully you remember from the last video that we were talking about the fact that the alkenes are more reactive than the alkanes. So typically the alkanes are very unreactive. There's only a very small number of reactions that they undergo, and we need to sort of push them and have special conditions to make them happen. Now, this is largely because the bond enthalpies, the strength of that single carbon-carbon bond is very strong. It takes a lot of energy to break, so it's going to have very high activation energy. And the other thing is that when we're talking about these hydrocarbons, such as propane, what we're looking at is there's a low electronegativity difference between the hydrogen and the carbon, which means it's not very polar. Okay, so the electronegativity difference between carbon and hydrogen is very low. So the bond between them is largely nonpolar, much like the molecules are nonpolar, which means that we don't have a polarity or somewhere where we have electron density being drawn towards one or the other. So because of this low reactivity, we have two types of reactions that we're going to look at. One is combustion, which we've talked about, remembering that for complete combustion, our products will be carbon dioxide and water. For incomplete combustion, we get mixtures of carbon monoxide and carbon. Hopefully you're familiar with those by now and good with writing the equations. The other one that we're going to look at is substitution reactions, and we're going to look at that in a bit of detail because there's quite a few things that you need to make sure that you have, that you've recorded it well in your notes, because it's one of those things where you are expected to recall a fair amount of information, and we can't do it any other way. So the substitution reactions of alkanes that we're talking about is essentially where we swap one atom, so we're swapping one atom on a molecule, so one atom on a molecule for another atom or group of atoms, for a different atom or group of atoms. Okay, so in this case, essentially, our methane here, all that we have that we could swap out is a hydrogen. Okay, and that's exactly what we do. We're going to swap a hydrogen for a chlorine, and we end up with the chloromethane. Okay, so we're replacing one atom with another atom or group of atoms. Okay, because it can be more than one. Okay, so to add different functional groups. Generally, in this case, the one that we're going to look at most within the IB course is the swapping of a hydrogen from an alkane for one of the halogens. Usually chlorine, but also bromine, fluorine will also undergo these reactions, and we look at a lot at bromine as well. Okay, so for this to occur, the covalent bond between the carbon and the hydrogen, so we would need to break this one. Okay, or I guess in this example, it would be better to say that we need to break perhaps the one with the solid wedge. So this one here. Okay, but we need to break one of these bonds, and then we need to break this bond as well in order to be able to rearrange them to form the chloro-substituted alkane. In order to do that, we need to look at the way that the bonds break. And what this means is we look at bond fission. So fission means to break apart. Okay, so we're not, fusion means to bring together, but fission means to break apart. So when a covalent bond breaks, there's a couple of ways it can happen. It can break so that we end up with the electrons, because remember that if we have carbon has 4 and then forms bonds with hydrogen, we get 1 electron from each atom involved in the bond. Now, this bond can break one of two ways. It can break giving the electron to each of the ends, so 1 each, or it can break giving it both electrons to one part of the molecule. Where we have both bonding electrons going to one atom, we get the formation of ions. Okay, so these are ions here where we end up with a positive and a negative side. Okay, so this we will tend to look at a little bit more in higher level where we talk about carbocations and carboanions, because you may remember we've said that carbon doesn't tend to form ions very well, and it doesn't. So these happen under special circumstances. Okay, and we will look at that in HL. In SL, we're going to only look at this one here, which is homolytic fission. Again, homo means the same, so they're going to split evenly. So when we have a non-polar bond or bonds with low polarity, like we see in alkanes, what happens is each atom gets one of the bonding electrons. So in this case, B will get one and A will get one. And when we get that, we form this species here. And this dot, we use a dot to indicate an unpaired electron. So an electron that is unpaired, okay, which means it will be quite unstable. And we refer to these as radicals. Okay, and you may have heard of the term free radicals before. So homolytic fission will happen when we have the halogens. So remembering that our halogens form Cl2, F2, Br2, I2. Okay, so they're all covalently bonded with a non-polar bond that's pretty much exactly the same whichever way we look at it. Which means that when this bond breaks, each atom will get one electron. And we show that by looking at what we call these fish hook arrows. Okay, you'll notice that they're not a double-headed arrow. They're not like that. They have just one head on them, and this shows movement of one electron. Okay, so this is showing that from here, from in this bond, there is one electron going to this chlorine, and from in here in this bond, there's one electron going to this chlorine. So when this bond breaks, in the presence of UV light, which we'll talk about, we get two radicals formed. Okay, because each one has taken one. And if we think back to our Lewis dot structure, this makes sense. We've got this one unpaired electron. Okay, which makes it, by definition, a radical. And when we started learning about chlorine, we said that it forms diatomic molecules because it doesn't like to have this unpaired electron. So you can imagine that this unpaired electron makes radicals very reactive. Okay, and you may have heard of them before. So we've heard about, there's a lot of stuff in the news and about eating healthy and living healthy about antioxidants. And it says that it soaks up free radicals in your body and things like that. And when they're talking about free radicals, they're talking about these species that have an unpaired electron, okay, that is very reactive because they have a tendency to steal electrons off other atoms, which can then cause other things to break down. So you can imagine if a free radical comes in and gets to your DNA and starts ripping electrons out of the molecules in your DNA starts to fall apart, and that causes disease and damage. So free radicals tend to, because they have an unpaired electron, they really want to get an electron from just about anywhere, so they'll tend to rip them off. So the reaction with a free radical, as soon as it comes into contact with another molecule, will generate another free radical. So if you look at this one here, if a chlorine radical comes into contact with a hydrocarbon where we've got a carbon-hydrogen bond, what will happen is that the chlorine will now jump in there, forming a new carbon-chlorine bond, but it'll kick out the hydrogen and leave it with a radical. So let's have a look at this in some examples. Methane, okay, so remembering methane is CH4, it's the first of our homologous series of alkanes, okay, can react with bromine under a substitution reaction. So we're going to remove a hydrogen and replace it with something else. And that something else in this case is going to be Br. So the BR-BR bond is weaker. We can see that by its delta H value here. It only requires 193 kilojoules per mole to break than what our carbon-hydrogen bond is, requires 435 kilojoules to break. Once we have the formation of our radicals, those radicals then can then react with methane, which will give me this methyl radical, okay, radical showing here, and hydrogen. Okay, so it would be a formation, a homolytic fission for the formation of ions. This one doesn't happen very often, okay, but this one does. Then, okay, so in the presence of UV light, this homolytic fission can happen for bromine, i.e. in sunshine, okay, where we've got UV. Okay, this process here, where the homolytic bond of a halogen breaks to give us two radicals, is what we call the initiation step, how everything is started. Once initiation has happened, okay, so now we have radicals running around in our system, it moves on to propagation. And hopefully you know that propagation means to grow, okay, so we're going to end up with more radicals. So the bromine radicals then come along, they can collide. So remember in here, I've got a flask and I've got some methane and I've got some bromine, okay? So these guys can collide. If this radical collides with a methane molecule, it's going to swap out, pick up a hydrogen, forming HBr and generating a methyl radical. That's one propagation step. Because we've now generated this methyl radical, it can actually come into contact with a Br2 and we'll get CH3Br and regenerate a bromine molecule, which can now go and hit another CH4 or hit a CH3Br and just keep making radicals, which can then collide and make new radicals. So there are many different propagation steps. In exam questions, they usually ask you to provide two. Okay, which allows the generation of the radicals to continue. So after we've had propagation, so now we've had initiation, we've had propagation. Now, and there's multiple ways this can happen, okay, in one flask. Eventually, what we start to see is termination, where if two radicals come together, these unpaired electrons now become paired and we form a stable molecule. So you can have two bromines coming together in the example that we looked at to form Br2. You could have a CH3 radical colliding with a bromine radical, which would form a stable bromomethane. Or you may even have two methyl radicals colliding, which would actually form ethane. Okay, so there's a number of ways that our reactions can terminate. Okay, so if we increase the concentration of bromine, so we keep the bromine high in our flask, we can end up with, instead of just having one substitution reaction happen, okay, where I end up with bromomethane, if there's still bromine around, it can continue to react. So depending on how long and how much bromine, that we can end up with dibromomethane or even tribromomethane, or eventually, if we keep the concentration really high, we could even end up with tetrabromomethane. So when we talked about forming halogenoalkanes from addition reactions, we said it was more specific and easier to control than substitution reactions. And this is why. Because if there is a large concentration of bromine and the reaction is allowed to continue, we can end up with a mixture of products with either 1, 2, 3, or even 4 halogens attached. So adding across the double bond is often a much more efficient way for us to make halogenoalkanes. So essentially, pretty much any alkane will undergo substitution. It doesn't have to be methane. It can be ethane, propane, or otherwise. Okay. You can get chlorine reacting or you can even have chlorine, bromine, fluorine will also react in this way. So just a quick point, hopefully now you have said, but hang on, when we did the bromine test, you said that it would decolorize in the presence of an alkene, which it does because it adds across the double bond. But if we're saying bromine can react with an alkane, wouldn't it decolorize bromine as well? The answer is yes, but only in UV light, okay? Because the alkanes need this UV light in order to do the homolytic fission of the bromine, okay? Without UV light, there's no energy to get this process started. So if we do it in the dark or out of the sunlight where there's no UV, we'll still get no reaction occurring with our alkane. So it's always a good one to check. IB will usually specify if the reaction is done in the dark or not. Okay, so this is something that I'm sorry you're just going to have to memorize. So you should all create a study sheet or a flashcard or however it is you go about memorizing things for each step of the homolytic fission reaction. Okay, so what you need to do is have an initiation step, which will always be in the presence of ultraviolet light and give 2 radicals. Propagation steps, there are a number possible. Forming of the alkyl radical and HCl and the chlorinated alkane and a Cl radical are the 2 common ones. So I would recommend these ones being the ones you memorize. And then you have any number of these 3 termination steps. But the overall reaction is also our Cl2 with chloromethane giving our chloroalkane. I'm going to stop this video here. It's been going for long enough, but please make good notes on this. And if you are finding it confusing, be sure to ask questions in class. This always turns up on exams.